We now turn our attention to clusters of galaxies. Well, they're certainly the most conspicuous parts of the large-scale structure and were the first to be recognized as somehow distinct units. Typically, clusters have sizes of few megaparsecs and contain hundreds or thousands of galaxies with masses of 10 to the 14 to a few times 10 to the 15 solar masses. They are all gravitationally bound, but they may not be fully virialized. As you remember, the free-fall timescale for clusters is measured in gigayears, and so many clusters are still forming. In addition to the obvious stars and galaxies, clusters are also filled with a hot X-ray gas, which was partly expelled from galaxies and partly accreted from the outside, and it's kept on the X-ray temperatures because of the deep potential well. But the dominant component, of course, is the dark matter. Of all galaxies, only maybe 10 or 20% are found in clusters. The rest are just covering large-scale structure in general, and the majority of galaxies are really small groups, just like the local group, with Milky Way and Andromeda dominating and a whole bunch of dwarf galaxies around us. There is one important distinction, though. The early type galaxies, ellipticals and S-zeros, tend to concentrate in clusters more than in general field, and there is relatively few spiral galaxies in clusters. This is reflecting processes of galaxy evolution, and we'll talk about them a little later. So here is the picture of the nearest cluster to us, Virgo cluster. It is the center of the local supercluster. It's about 15 to 20 megaparsecs away. The picture on the left is the X-ray image in false color. The picture on the right shows where the galaxies are. And you can see there is broadly speaking, a good correspondence. About 2,000 galaxies have been cataloged in Virgo cluster, but most of them are tiny dwarfs that you have difficulty actually pointing out. The next famous cluster is the Coma cluster. It is 5 to 6 times further away, and it is richer than Virgo by a considerable factor, and it's comparable to the kinds of clusters that we see at larger distances from us. Here again, I show you the optical image in the upper right. You see there are 2 dominant galaxies there, and the X-ray image in the lower part, and you can see it's much smoother than the one for Virgo, because Virgo is dynamically unclustered, it's still falling together. Coma is relatively much more evolved. The picture on the right just simply overlays the X-ray contour map on the optical image. And on the opposite side of the sky, roughly, is the Perseus cluster, and that is about 4 or 5 times further away than Virgo, not as rich as Coma, but it has this nice little chain of galaxies in it, one of whom harbors a very powerful active galactic nucleus. As we look deeper, we find more clusters, and by and large, some of them look pretty much like clusters near us. Again, this is because cluster formation timescales are broadly comparable to the age of the universe, so you expect to see more or less similar kind of clusters at any given time. Not very early, because they don't have time to form yet. This is an intermediate distance cluster at redshift 0.43. Picture on the left is the visible light image from Hubble Space Telescope, and picture on the right is the X-ray image from Rosetta satellite. Clusters are now known out to redshifts of maybe 1.5 or so, and there are hints of cluster-like structures to much higher redshifts yet, past redshift of 5. But this is one of the most distant clusters proper that we know, at redshift about 1.23, and it again looks reasonably well formed. So how do we look for clusters? The most traditional method is just looking for overdensities of galaxies on the sky. And this is how most of the initial catalogs were compiled. In fact, we use every one of the cluster properties as means of finding them. So in the optical, this will be simply a density of galaxies. And nowadays, the way this is done is a galaxy map on a sky, a projected density map on a sky, is smoothed, and algorithm of some sort is used to identify the overdensities. Because clusters have a large population of red early type galaxies, and because of the redshift, it makes sense to use near-infrared bands rather than the optical ones as we go to higher redshifts. This is a fairly straightforward way, but it's very vulnerable to chance superpositions. That you can't sometimes tell whether it's really a cluster or it's just superposition of several smaller clumps along the line of sight. Probably the most famous of optical cluster catalogs is the Abell catalog, which was initially compiled by George Abell from first Palomar sky survey, simply looking at photographic plates with a magnifier. Later on, this was extended to the southern sky and has about 4,000 clusters. This catalog has been a mainstay of cluster studies for a long time. Abell defined an operational criterion. What is something that he will call a cluster? There has to be a certain number of galaxies within a certain magnitude range and radius, and it's a reasonable set of criteria, essentially a density contrast. He divided clusters in richness classes, depending on how many galaxies he could count in them. He also had distance classes because at that time they didn't have redshifts to all of them. Abell's catalog had some problems. I mean, it's not a statistical sample, although people often forget that. Abell himself defined a small subset of it that he thought would be complete, suitable for statistical studies, and everything else was extra. So people complained about subjective nature of the catalog, and these days nobody's doing this by hand anymore. We deploy algorithms that look for galaxy over densities using some well-defined criteria, and typical modern catalogs of clusters of galaxies using sky survey plates would have tens of thousands of clusters in them. The next method is using X-rays. Clusters do contain large amounts of hot gas, and they're very conspicuous on X-ray sky. Basically, in the X-ray sky, you see point sources, which would be active nuclei or maybe stars of some sort, and extended sources, which are clusters of galaxies. Here, the superposition problem does not play a significant role. In part, this is because the X-ray emission is proportional to the square of the density. And that means you really have to have material in one place to have a significant brightness in X-rays. But even so, X-ray method does not select clusters by mass, just like optical method does not select them by mass. Related to this is the Sinaev-Zeldovich effect, where we use combination of X-ray measurements and microwave background maps to find clusters. Now, you may recall what Sinaev-Zeldovich effect is. We talked about this when we talked about the distance scale. If you look through a cloud of hot gas towards the microwave background photosphere, those photons sometimes encounter a hot electron and get inversely Compton scattered, meaning they get some of the electron's energy. As a net result, the spectrum of the microwave background as seen through this cloud of hot gas shifts to higher energies. And now, depending whether you're observing it in radio, blueward or redward of the peak of the black body, you can either see a bump or a dip in the sky. And that bump or dip corresponds exactly to the X-ray signal. Finally, weak gravitational lensing provides, at least in principle, means of detecting clusters, and this time by their mass, because that's what lensing is actually sensitive to. As you will recall, weak lensing would show distorted images of galaxies due to some foreground mass concentration, such as cluster. And by looking for such signals in shape patterns of background galaxies, you could find large masses, whether or not they actually have any light or X-ray emission. As it turns out, to the best of my knowledge, there was never a cluster discovered using this method that wasn't already seen or easily seen through optical or X-ray. So what can you do with clusters? We can measure some of their properties, more about those later, but you can just look at them. And typically in any empirical science, you begin with the morphology. So Abell initially classified clusters simply on the basis of their appearance. He noted that some are well relaxed looking, symmetric, and the others still look like raggedy. Now we know that that corresponds to dynamically well-formed versus still forming clusters. Now in 1970s, Bouts and Morgan introduced a different classification. This one was not really based on properties of cluster per se, but whether or not it had a giant dominant elliptical galaxy in the middle, as many of them do. This turns out to have some significance for galaxy evolution in clusters, but again, it was relatively superficial. Then further shifting focus not on clusters' appearance, but on their galaxy population, Omler also classified them according to the amount of spiral versus elliptical galaxies in them. That directly relates to the galaxy evolution processes in clusters. And Rood and Sastry had one of these schemes, at which point the meager amount of information that's actually present in these optical appearances was really exhausted. However, we do now have good physical understanding where all this comes from. Just a note about those central dominant galaxies in clusters, or CD as they're called. They're giant ellipticals, but unlike other giant ellipticals, they have an extra fuzzy envelope at large radii. Now we think that those extra fuzzy envelopes do not really belong to galaxies, but to the clusters themselves. That they're piles of stars stripped away by tidal interactions of galaxies in the cluster, and they accumulate at the bottom of the potential well, and the big galaxy also happens to be co-spatial with them at the bottom of the potential well. So it looks as if it has this fuzzy envelope. So there's some interesting trends. Well-relaxed looking symmetric round clusters tend to be dominated by elliptical galaxies. Ruggedy, flattish looking clusters are those where they're dominated by spiral galaxies. And even within given cluster, there is a segregation that the early type galaxies, ellipticals and S-zeros, tend to congregate in the inner portion of the cluster, where spirals are predominantly found at the outskirts. Now we have good understanding and explanation for these effects from galaxy evolution. As far as the appearance is concerned, the round, smooth ones simply had enough time to relax into virial or almost virial distribution, whereas the lumpy, flattish, non-uniform ones are still coming together. And those central dominant galaxies probably are, in part at least, product of mergers of many smaller galaxies that built them up. So next time we will talk about contents of the clusters of galaxies.